to do.
Having time off for Easter and so on, so yeah.
Morning everyone, just doing a sound check. Let me know if the sound's coming through okay and if there's an echo or not. Hi everyone, just doing a sound check right now. Let me know if the audio is coming through okay and if we're echo free today. Again, if someone could put in the chat if this audio is coming through clearly and if we're free of echo, that would be great. Thanks so much. So we're actually going to start a little bit earlier today. I'm going to wait all the way to 5 parts to get through. Intro video. So you have 2 more minutes of peace, and then we're going to begin. And again, just write in the chat if there are technical difficulties that I'm not noticing. Hopefully, if I spot them, then we can pretty quickly. And I think we're ready to begin for the week. Okay, let's get this started. It's now been 2 weeks since I last heard from you. If you get this message, I've attached 2 communiques that I managed to intercept from Duck. I'm only nervous now that they'll find me before I have a chance to deliver it. I'll be back. I'll be back shortly, but what's that sound? Oh my god! I think they're sounding! It's Duck! They're coming for me! Oh my god! Oh my god! Send help! No!
A. B. You must be C. With you're an individual of certain talents. Our director has told us that you may be able to crack the code. Would you do it? Would you be able to do it?
I hope that for all of you that was a really fun way to come back into the next half of semester. You've got me for 1 more week, and then you'll have Janjong. So hopefully enjoy the next couple lectures, because they're the last you'll see of me in lecture, at least for a little. As you saw in the video, our first assignment has been released. It's pretty exciting, but it's also significantly challenging. And I know many of you might look at it and think, wow, this looks really difficult. There's a lot of text. There is a bit of an entry barrier, so you're going to have to spend a couple of times reading over the spec, getting used to it, figuring out what's going on. We've got some video content that's already been posted online to help you out with this, and a little more will come. But know that once you figure out how to get started, it'll kind of snowball and will get a bit easier for you. Why did we pitch it at this level of difficulty for you? We want to give you a real challenge and something that's analogous to what you might do in the real world. This assignment is very, very close to an actual research project. While we've made things significantly easier for you, added testing and a lot of guidance, know that as you get the assignment, you'll be developing real skills and something you can be proud of. Another question I had about the assignment was, do I need to read the research paper that the assignment is based on? The answer is definitely not. You do not need to access or to spend time with any of the research level content. It's just there so that you can see what this is based off on, and so you can feel kind of proud of yourself in a way that what you're doing is something that is at such a high level, even though it should be accessible to you with the training that you've already got. Again, if there are any questions with the assignment, all of your staff are here for you, and we are ready to help out. Ready and raring to go. Use Piazza, use Grok. At the very start, when you're having trouble understanding it, use those resources, come to consultation hours, and we'll be able to explain the different parts of the assignment better to you. And with that, I will take us to our lecture slides, which will take me 1 second to pull up, because they mysteriously disappeared from my stream. There we go. Okay, so as usual, we're going to start our week with a little bit of computer science history and a figure relevant to what we're going to be learning. Today's figure is Don Knuth, who is known as the founder of algorithmic analysis, and that's what we're going to be focusing on for the rest of this week, is a couple of different algorithms that Don Knuth actually wrote about in his beautiful 3-part series, The Art of Computer Programming. If you get a chance, go down to the library, just look through the pages and see what a wonderful set of volumes they are, written by this man who contributed so much. Like many of the other course, he did spend time at Bell Labs, and he also worked for the National Security Agency as a cryptographer, where he met some of the other figures who we've been familiar with. Other interesting facts about Don Knuth is he's also an organist and a composer. He's still alive today and working as a faculty member emeritus at Stanford University. And you'll see in the bottom left-hand corner, there are some Chinese characters. That's actually Don's Chinese name that was awarded to him in recognition of his merit by one of China's top mathematicians. And he subsequently embraced this name and felt that it was an opportunity for him to become better known amongst all the programmers of China, a country of which he was very fond. Now, lectures this week may run a little longer than the prescribed time. It's because we lost a bit of time in the last week with the break, and also we did take a lecture for the mid-semester test, and I want to make sure that you get as many contact hours as you deserve. With regards to the mid-semester test, yes, it was quite challenging. Much like the assignment, it's designed to test your mettle, show you where your strengths are, and show you where your weaknesses are. I wouldn't worry too much about grading. Have more information on that pretty soon. We're just sorting out some final things, and then we'll release grades, and I'll also have a bit of a talk about it in next lecture about how you all went and what the problems were, and then there'll probably be a separate solutions video given where we are in terms of lecture timing. And is my clicker going to work today? Looks like the answer is no. Okay, no clicker. Oh, one last thing about Don Knuth. If you look up any of his algorithms or any of his books and you spot an error and write to him, he'll actually send you a check. And these checks are considered very valuable by computer scientists, not for the amount, which is typically 6, a power of 2, but for the prestige that comes with having spotted an error in one of these famous sources. already spoken a little bit about the assignment, so we'll move on to our course content. Where we left off last week was talking about linear search. That is the problem of if you have an array of n elements and you're looking at an element with value x, how do you find this element? And the first algorithm that we came up to tackle this was linear search, a very simple algorithm that looks like this. Now remember, this was the version of the algorithm with all these assertion statements in it that we hadn't really discussed yet. We're going to get to today. So let's start off with making some statement about something that we want to be true in our program. What this statement should be is part of the invention of the algorithm, so don't worry if you can't come up with it on your own yet. This is to illustrate how we'd prove the correctness of an algorithm. In this case, our proposition is as follows. Well, we're going to call our proposition P, and we're going to write it in this slightly fancy mathematical notation, but the idea is fairly simple. We're at position I, which is somewhere within the array, so that's the first half of this statement. 0 is between, I is between 0 and n, so it's located within the bounds of the array. And x is the value that we're looking for is not in the things that we've seen so far. I is going to keep track of where we are so far. So we start I at 0, and all the elements between 0 and 0, that's an empty set. Well, what about when we make I 1? All the elements between 0 and 1. We're going to have this proposition that x is not in the things we have seen so far. So x is not between 0 and actually I minus 1. Sorry for that index error. And we're going to be able to use this statement that's true for the duration of our program in order to be able to prove the program is ultimately correct. Let's see how this works. Okay, there's our code again, and I'm going to break it down into two halves to make it a little easy, so I'm going to hide the bottom of it for the moment. Let's start off. Remember our statement. I is that's within the bounds of the array, and at all times the value that we're looking for should not be anywhere that we've already seen. So I minus 1, from 0 to I minus 1, all elements, none of them should be the one we're looking for, x. So we set I to 0, and then we make our statement. We assert again that P is true. We know our proposition is true because we haven't seen any elements so far, and there is a 0 index in the array, so everything's true. Okay, great. Next step. Let's while loop. Let's go through the elements in the array all the way from I is 0 to I is less than n, and we're only going to do the loop while the ith element is not the one we were looking for. At this point, let's check our assertion again. Given these loop conditions, do we know for sure that I is between 0 and n? Yeah, that's guaranteed to us by the guard. And we also are guaranteed that the ith element is not x because otherwise the loop would have terminated. Notice the condition in the is the same as the second half of this new assertion. Then we increment I. We go to the next element, and if we go to the next element, let's assert P again. Let's make sure we're still within the array and that we haven't seen the element that we're looking for between A0 and I minus 1. Well, we know that this must be, and so we can continue to the next step of the algorithm. So that is our entire while loop. What happens when we exit the while loop? Well, when we exit the while loop, one of the conditions in the guard must be false. So either AI must be x, and remember that our proposition was AI from 0 to I minus 1 is the element. So it's okay if AI has it as long as it's not in the. So when the loop terminates, either I is equal to n, which is the negation of the guard, or AI equals x. One of those two conditions in the guard must be false. So when the loop terminates, we know that we fall into one of these two cases. So the first case is where the first half of the guard was not true. If I is bigger than the size of the array, then we do our assertion again. I is between 0 and the size of the array. Given that I is greater than or equal to n, and I is also less than or equal to n, I must be n in this case. So P is still true, and all the other stuff that we added on, and I is greater than n. This means that if we reach the end of the array, because I is all the way at the end, and we're still saying that the ith element isn't x, because we're outside the array, that means for sure x can't be in the array, and we return not found. We've proven that if we get to this point in the program, the correct answer must be not found. And the way we do this is by checking the assertion at each stage. What about in the other case? What about if it's the second half of the guard that's false? If x. Well, then we're in the bottom part of this conditional statement here. So we assert P, so I is within the bounds of the array, somewhere between 0 and n. And we know that I is not outside of the array because otherwise we wouldn't have been in this second branch of the conditional. That means that the ith element must be x. We've proven it. We now return I, and we know that our algorithm is correct. This idea of including assertions everywhere within the program, everywhere the program can possibly get to, and checking after each modification where the assertion could have gone false, that the assertion is still true, allows us at the end of the day to say that because the assertion is true at all these times, it leads to this implication of the correctness of our program. So one of the challenges in designing an algorithm is figuring out the right assertion to make this work. As I'm not expected to always be able to do these proofs on your own, it's part of the process of inventing the algorithm. The other thing that we need in order to prove the correctness of the algorithm is to know that the while loop will eventually terminate. In this case, it's fairly simple to see. I starts at 0, n is a finite positive number, and so if we keep incrementing I, we will make progress towards our loop termination, and it will eventually end. So these assertions were a really powerful tool to prove statements about algorithms and to actually prove the correctness of algorithms themselves. You can also include them in your C programs. I'm not going to go through the syntax now, and of course the syntax we just saw was not C. But if you include the assert.h header, you can start to do this in your own programs and have inbuilt ways inside the program of proving their correctness. So now we've got a couple of questions about how efficient our algorithm is. So I will pull up Slido, and you'll all have a couple of seconds to answer a few questions. So the first question, what is the best case runtime of linear search? This algorithm that I just showed you, what is the fastest that it can go? Okay, I'll give you a few seconds to pull up Slido if you haven't already, but I want a couple more responses. And the majority has one can turn on their camera and wants to give the answer why. Why is the correct answer O of 1? Why did you pick that? That would be great. Anyone who picked that, feel free to turn on your camera and say. There are at least 15 of you who've given the right answer. One of you can come and switch on your camera and explain why O of 1 was the right answer.
It's if you find the element right at the start of the list.
Yeah, that's right. If the element x that you're looking for is the very first element, then your program is going to terminate right away as soon as you search for the element. Okay, so we've got our best case. What about the average case? What is the average case runtime of linear search? Again, a couple seconds on Slido, and we've got one more of these after it, so keep your window open. We're 22 of you who answered last time, so I can get at least a few more answers. So this answer might actually surprise a few of you. Big O notation, as we're going to see pretty soon, actually ignores the constant. So a constant of 1/2 outside is the same as having a constant of 1 out the side when we're using asymptotic or big O notation. And we'll prove this rigorously in a few minutes. Although, on average, you do expect to find the element halfway through, because we're relying at the end of the day on the number of operations the computer is doing to figure out the actual runtime, we often end up throwing away this constant because it ends up being less relevant to the overall structure of the algorithm than the fact that we're going to have to go through the array in a linear fashion. And last question for Slido for the day. What is the worst case runtime search? Is indeed still. So in this case, the asymptotic behavior, the behavior of the algorithm, in the average case when you run it, and in the worst case when you run it, have the same type of behavior. Now that doesn't mean if you put something halfway through the array that you're looking for and run it, it will be just as long as if you put something at the end. This is talking about the behavior of the algorithm as the inputs get large. It's not actually saying for a specific example how many seconds will it take. And with that, we're ready to go back and learn about asymptotic analysis and how we actually prove these results. So we've found our best case, our worst case, and our average case. And these three types of cases are going to be the way that we analyze most algorithms. Note that the best case is overly optimistic. It is very, very rare that when someone provides input to the program, they'll provide exactly the input that makes it run the best and terminate straight away in the case of our search. Much more common, you'll be thinking about the average case or even about the worst case. Hope for the best, or at least average. And one reason why we might think quite a lot about the worst case is because we can't always assume that the people entering data into our system have the best intentions at heart. Maybe they want our algorithm to run slowly to slow our computer down. We have to plan for any eventualities. It may not even be a malicious user. Perhaps it's a silly user, or perhaps the data is skewed in a particular way that makes it run really badly. This type of analysis is going to become really important to make sure that we're designing algorithms that work for us real-life scenarios. And it is finally time to formally define big O notation. We're going to care about the rate of growth of our algorithms, not about the number of particular seconds that things take to run. While in the real world, ultimately at the end of the day, we are going to want to go back to clock time, when doing the analysis of the behavior of the algorithms, we want to know roughly how they grow. This gives us a really good rule of thumb for figuring out whether is overall a better design than the design of another algorithm, rather than just focusing on the implementation details in the computer. And I've said this before, but hopefully by now it's starting to sink in. So with that, let's get to it. This is going to be a little bit mathy, but I know you can make it through. Now, as John Lennon said, imagine all the functions. Yes, all the functions, every single possible function in the world. So that would be like x squared, x to the 3, 3x plus 2, 2x plus 5, every single function that you can possibly imagine. Have all the functions in the world. Now, divide each function into a group, into a set, according to how they grow. And we have this funny looking mathematical definition of what these sets are going to be. So each set is going to be O of g of n, where g of n is some reference function. It's some function that we are comparing f of n to. And all functions that can be compared in the same way to the reference function are in a set. A function might also appear in multiple sets because it may compare favorably to more than one function. For example, the function n, f of n equals n, grows more slowly than n cubed. So if we are asking what are all the functions that grow more slowly than n squared, that's going to contain n. And if we ask what are all the functions that grow more slowly than n cubed, that's also going to contain n. But remember, on either side of this equation, we can have any number of functions, and the definition will still make sense. Now we have the second half of this slide. This looks pretty complicated. Turns out not to be as difficult as it seems. Let's look at the translation. We're not only talking about functions of integers, we are talking about every single possible function in the universe of functions. Now think exceptions with discontinuous functions, but well outside the scope of this course. Thanks for the question, Harris. What is the translation of that weird mathy looking bit at the bottom? F of n is an element of big O of g of n if, for all values n larger than some threshold, there's a multiplier that guarantees that f of n is smaller than g of n. We're going to unpack this with a few examples because it's a little abstract, but essentially what it's saying is ignore small values of n at the start of the function. The function might behave weirdly, like you've seen cubic and quadratic equations before in your life. Turn around a little, that zip zag, but after you get to some threshold behavior, they like start running off into the distance. And that's the part of the function that we're going to care about. Once the function is running off into the distance, is it always going to be less than some constant multiplied by another function? Let's do some examples of this to make it much more concrete. I get that this can be a tricky definition to visualize abstractly. Just a note on pronunciation. There are a few ways of talking about it. Some of them are less correct, but it doesn't really matter. Everyone knows what you're saying. But the way we pronounce this is we say a function f is big O of g of n, or the function f is of order g of n. If you really want to be formal, you could say f is an element of the set bounded by big O of g of n, but we really don't need to go that far. One other note is once you've picked your value for c and n0, this threshold value into the distance, you've got to stick to them for that particular proof, changing them. The intuition here is that we're going to all the small values of n, and once the function stabilizes, it's going to stabilize to less than some multiple of g of n. Here's our first example. Let f of f1, let's call this, let f1 be 2n. And we can say that f1 of 2n is an element of O of n. Why? For all n is larger than 1 and c is 2, 2n is going to be less than or equal to big O of n. And let's actually work this out. So when we choose n as 1 and when we choose c as 2, we're saying that f of n is bounded by 2n as long as n is bigger than 1. And if we do the substitution, that's simply because our function is 2n itself. So 2n is always less than or equal to 2n. Makes sense. That was too simple. Once we get to some more complex examples, you'll see how it can actually result in a more difficult proof. Here's another one. Let f2 equals 15n plus 27 root n minus e log n. This is just some random function. And we want to prove that this is still big O of n. And we'll choose our values of n1, n0 is 1, and c is 42. Now let's see how the proof works out. Remember, we want to show once n is larger than 1, our value of n0, and if we're bounding it by 42n, because that's our value of c, at the point after we reach n equals 1, this f2 is always going to be smaller than 42n. Okay, here's our proof. On the left-hand side, we have our function f1. On the right-hand side, we have our function c multiplied by g of n. And g of n, in this case, remember, just the function n. So, to start our proof is we're going to divide everything by 42. Why do we do this? You'll see momentarily that it makes the proof work out. Requires a little bit of ingenuity, but it works. Now, also remember, negative e log n is going to be less than 0 for n is larger than 1. Now, 27, we get 42 on the left-hand side. So that's 42n on 42 minus something is less than or equal to 42 on 42n. So this boils down to saying n minus something negative is less than or equal to n as long as n is a positive number. And we know that is true. If you take x minus 1 is always going to be less than x, no matter what x is. And if you take x minus 2 is always going to be less than x, no matter what x is, as long as x is a positive. Our proof, we know that it's the case that for all n that are larger than 1, so as long as n is positive, and if we set c to be 42, then we're guaranteed that our function on the left is going to be smaller than or equal to the function on the right. And so we know that f2 is big O of n. Oh, and there's a slight typo on that slide where I accidentally wrote f1 again. As I said before, O of g of n does not provide a tight bound because n is less than n cubed, n is less than n squared. There are a whole bunch of functions g of n that are bigger than our function f on the other side of the equation. There are ways of getting a tight bound, so you've picked the smallest possible function. But those are going to be represented by big theta instead of big O, and we might see that either tomorrow or the day after a little bit. There's also one for below, big omega, but that's outside the scope of the course. Got a hair in my cup. Okay, here's another example. We can also do some manipulations with O. And in this case, let's take two functions. F2 is the same as before, n as before. Do the proof showing that if f3 is the multiple of two of these, then f3 is going to be big O of n squared. And again, I've chosen my constants carefully to make the proof work out. How do you choose the constants? Eventually, you develop the intuition after doing a bunch of these proofs, and you see a whole bunch of techniques that you can use to make it easier to show that, say, your left-hand side is less than or equal to the right-hand side. And, oh, my camera dropped out for a second. Okay. Let's do our proof. Remember, I had right before, I've chosen c equals 84. So I'm going to do the same kind of thing that I did before, only this time I'm only going to start with the left-hand side of the equation to just illustrate it a bit better. So let's divide my function by 84. I have 39 84n squared plus 54 on 84 n to the 1.5 minus some number on 84 that I don't care about for the time being. Why did I choose 84? Well, you'll notice substituted in... Oh, there's a slight error on here. F3 should, the first two terms should be multiplied by 2 there. Anyway, ignore my mathematical typos, it still works out. And I will make sure in the recording that I fix those. So if I've multiplied the whole thing by 2, so remember there's meant to be a factor of 2 out the front of 15 and a factor of 2 outside of 27, then 30 plus 54 equals 84, which is why I chose the number 84. So if I were to somehow be able to add them together, even though they're different powers of n squared, then I'd get that 84 and I'd be able to do that cancelling down thing I did right before. So we know that F3 on 84 is less than this thing on the right-hand side now. This thing on the right-hand side is not our big O, this is just part of the proof. What I've done here, I've changed the n to the power of 1.5 to n squared. Why can I do this? Well, because I'm using round. I'm n to the 1.5 is less than n squared, so F3 with n to the 1.5 is obviously less than the version where I've put an n squared instead. And now I can add the two and I do 30 on 84 n squared plus 54 on 84 n squared minus some number, and as before, n is going to be larger than 1 just to make sure that that part is positive. So when n is larger than 1, we now know that F3 on 84 is less than n squared minus the log term, which itself is less than n squared because the log term is going to be negative. So we just rearrange this, we take the 84 that was dividing F3 and we move it to the other side, and then our proof. F3 of n is less than 84 n squared, which is the same as saying F3 of n is less than 84, is less than or equal to C of n squared as long as n is positive, is larger than 1 and C is 84. Again, I'm going to remind you that O over G of n contains all the functions that have the same or smaller growth rate. So not only can the functions on the right-hand side change, so you can say 2n is less than n squared is less than n cubed, but 2n, it's not just 2n that's less than n squared, it's also 1n that's less than n squared, it's also half n, it's log n is less than n squared. All of those functions are in the same set of things that are less than n squared. Now, generally, instead of saying that 2n is less than n cubed or 2n is less than n to the 1000, we are going to try and pick the simplest one. So we'll say that 2n is less than big O of n. Less than or is an element of big O of n, sorry, or of the order of. Because it doesn't... Why would we talk about bigger functions when we've got something that's a tighter bound? So in this class, even when we ask you, like, what is it big O of, don't give us some, like, large function. Try and pick the one that's the best fit, the one that most accurately describes the behavior of the function, the tightest bound. You pick, so instead of n squared, we're going to pick like 2n, but instead of 2n, why not just say n, because the constant, and probably extra terms, so instead of saying n plus 5 about root n. That makes it more complicated. Contain as few functions as we need for the given purpose. And this will make our proofs and our descriptions simpler and easier to deal with, and enable a simpler comparison of different algorithms. Because ultimately, that's what we'll be able to different algorithms so that we know which one is a better fit for a given purpose. Functions, you've found a time bound for your big O. And I've already said that point, so I'm not going to belabor it again. This is just an example of different bounds that we could have chosen in this case. 2n log 2n is is big O of 5 minus 3. Yeah, an n squared function is bigger, but instead it's big O of n log n, because that more is a tighter bound and will enable us to compare algorithms more effectively without worrying about the computer or the particular input that they're running on. We don't anticipate 20 minutes of lecturing on big O notation, you'll be able to do these proofs from scratch. The idea here is to introduce you to the so you can understand. Hopefully soon you'll also be able to do some of these proofs, whether by the end of this course or in your next level algorithms course if you decide to take one. How does this notation let us compare algorithms? Well, if f of n is big O of g of n, and g of n is not big O of f of n, so this is just saying they behave differently, then for sufficiently large input, so as long as our n is bigger than n0, f of n is going to be faster than than an algorithm that is f of n is going to be faster than one that is g of n, which is pretty good news because that means some algorithms will actually allow us to solve our problems quickly. This is a graph of, for different sizes of n, let me switch my camera off for half a second, for different sizes of, for different orders of magnitude of growth, how things grow. On the bottom axis, we have the size of the input, and on the y-axis, we have the amount of time that it takes something to run. So on the top axis, the function that grows the most quickly out of the ones we've listed is n factorial, and the one that grows the slowest is O of 1, which is just a flat line, and above that is log 2 of n. There's also another way of thinking about function growth, and that is in terms of, a function line. So we can plot out a line just like a number line where we list all different types of functions. So let's put n at the middle. You could get O of 1 of n, but I don't have an algorithm offhand for that. So we know that n squared grows faster than n. And between n and n squared, there are a whole bunch of functions. 2n, 3n, 4n. There are a whole bunch of different ones. And as my little video goes on, we'll even see a few more of them. So what about other things that aren't necessarily polynomial? Well, slower than the growth of n, we have root n, which is still, I guess, a polynomial, but it grows much more slowly than n. Larger than n squared, we have n cubed, but we also have behaviors like 2 to the power of n. So we could, instead of increasing the exponent, we could instead increase the base. And then we have our n factorial, which we saw grow super quickly. And then we'd also have some functions on more on the left-hand side, such as log base 2 of n, or functions that grow even more slowly, such as log star of n, the iterated logarithm, which you can Google if you want to see a function that grows super, super slowly. Now, it turns out that log base 2 of n is going to be pretty important. Why? It seems to be just part of the fundamental structure of the universe that a lot of things work by doubling and halving, and log 2 is going to, particularly in binary, is going to represent this halving procedure for us pretty effectively. And we might even see a bit of log base 2 today. So this is our function line, and remember that in between all of these different functions, there are an infinite of functions. Remember our John Lennon, imagine living in harmony. So many functions there. And your job with big O notation is to find the best bounds or the right place on the number line to describe these functions. So we've got some exercises at home for you along with the assignment. Don't worry if you don't have time to get to these exercises just yet. We know you're super busy. But they'll be here waiting for you. So now that we've taught you the definition of big O, you're capable of proving the truth of some of these arithmetic statements. However, know that not every possible arithmetic statement about big O is actually going to work. So try these out, see if you can get the proof to work, and if not, provide a counterexample. There's also a book that I used in preparing for this lecture, Concrete Mathematics by Graham Dongknuth, who we saw earlier this lecture, and Potashnik, and I actually thought their description was pretty reasonable. A bit heavy mathematically, but if you want something extra, I'll put it out there for you. And there's a copy available in the library. The next question that we're going to focus on is, can we make linear search faster? It seems like it's a bit inefficient to have to search through all the things in the array. But at the same time, if we don't know where the object is going to appear and we don't have any more information, that might be a little difficult. So the answer to this question is both and no. And now for the next technical demo, it'll take me a second to set up, because I'm going to use a second camera, which I will need to connect. And it hopefully will connect. Yeah, great. You might get some weird views up my nose momentarily, but you will just have to live with it. Well, the first thing we could do to improve linear search is to terminate early. At this point where if we know we're in a sorted array, which gives us extra information because we know things are in order. So if our current element is bigger than the element we're looking for and we're sorted in increasing order, then we can terminate early. We don't need to go through the rest of things to know that it's not in the remainder of the array. Because it's sorted and we know the point at which it would appear, we should be able to exit early. But this only improves our best case, where things are sorted and we've already also seen the point at which we expected to find it. And we don't know that that's the case that we're actually going to find. Oh, and I've been invisible again. Let's make me uninvisible. Can we do better than assuming that we are in a sorted array? And this is where we get our live demo. So again, I would really appreciate if I could have one live audience volunteer to put your camera on. It would be a big help. And I will transition to an interesting tool display. Okay. So here in front of me, I have a copy of the 1991 Encyclopedia Britannica. If none of you have seen one of these before, this is what an encyclopedia used to look like. It has all these different entries ordered from, in this case, this volume, Do to Zwiak. So they're in alphabetical order. I will show you what that looks like. Here. So we have camera copy. There we go. Have our page. It's got all these different entries. Let me change the rotation on that as well. Different entries. There's verset, vertebral column. Wow, it really does not like this camera. Verse, etc. And you can see that on the back, this is the volume from Trudeau to Zwiak. Okay. So, thanks about the. You're right. I'll mute the other mic in a second. Just have to try and get things set up. Okay, the mic should be off now, and we should have about the echo there. Okay, now I want one volunteer who is willing to turn on their camera and help me find something in the encyclopedia. Anyone will do. I'll give you a few seconds to volunteer. Guys, making the lecture go longer. The sooner someone volunteers, the sooner we move on. It could be you. You could be the volunteer. Okay, given the absence of audio support, I guess I will have to do it on my own. But next time, I expect a volunteer. Yeah, I'm sorry, Nicholas. You know what? If you don't have the camera, you can do it audio. That'd be just as much help. Or Rose. Either of you two. Just turn on your microphone and guide me through. Thank you, Rosemary. I'm not sure how to say your name. Okay. Can you hear me? Or can I hear you? Say something. Not coming through. Okay, I will just do it myself then. Okay, let's say in my encyclopedia, I am looking for the entry for Turing. Oh, that's all right. Let's say I'm looking for... One way to do it would be to open up at the start of the encyclopedia and look trumpet, trungfish, truth value, and look at all the different entries on the page. That's linear search. What would be a better way of doing this? If you have your microphone and it's working, shout it out or put it in the chat if you know what I could do better. How could I more effectively and efficiently find Turing in here?
Use the table of contents.
Okay, so I could use the table of contents, but it turns out that this encyclopedia doesn't actually have a table of contents. It just says if you want to find something, they're in alphabetical order. Max has an idea. Start from mid. Okay, I'll open it up roughly halfway. I'll open it up to halfway here. Now what do? I've opened it up halfway and I'm at Warwickshire and Washer on my 2 pages. What do I do next?
The alphabet, then T, and then go to the other half.
So this is Warwickshire. Should I look at this half or should I look at that half?
The left half.
The left half. Okay, so what am I going to do? Am I just going to start turning pages?
Are you going to split it in half again?
Okay, split it in half again. I'm now at Verdun, Treaty of. Okay, what do I do? Left half, right half.
Left half.
Okay. Let's go. University College. Left half, right half.
Left half.
Okay. Let's do this again. I won't ask you too many times. UAR, we're still left half. Half, right half. Remember, we're looking for Turing. T-U-R-I.
Right half.
Right half, okay.
I think.
Yep. So that's only a couple pages here. Actually, I think we might have, I might have missed it in those pages. But you see this procedure works. Here we go. Finally, Turing, Alan Matheson. We found it. And so our procedure is to start in the middle, figure out which half we need to go to, then go to half of that half, figure out which half we need to go to, half of that half, and half of that half again, and keep repeating the process until we've only got 1 page left and we can't divide it into any more. And that is called binary search. And that's the program we're going to be looking at in the next lecture. But as promised, we are going to have to run a little bit long, so I'll take another 5 or 10 minutes now. If you want to drop off because you've got another class, that's cool too. So the key idea behind binary search is repeated range halving. We are going to find which half we need to go to, and then find out which half of that half we need to go to, and which half of that half, etc., etc., until we... The procedure looks roughly as follows in pseudocode. Take as input the topic. In our case, the topic was Alan Turing. Then store just all the pages inside book, open book to the center, look at the pages that we're on, go through all the entries. If the entry is looking for, return the entry. Otherwise, figure out if the topic is earlier in the book. If so, the book, set the left half of the book to the thing we're looking at and go back to line 3 and repeat the process. Otherwise, if the topic is late in the book, do the same thing with the right half. And if we've finished this process, it's not in the earlier half, nor in the later half, nor in the current half, we know the thing's not in there and we can quit. Now, this only works with a sorted input, but it did give us a huge increase in efficiency. I didn't have to look through every page to find where Alan Turing was. I could do just a few jumps and get most of the way there. The way we were talking about this seemed like it was a recursive algorithm, and it's true. You can represent this algorithm recursively, just as we were representing it iteratively in the last slide. So let's call this function findTopic, and the way findTopic works is for all our base case is look through the page, and if it's on the page, otherwise, if the topic is earlier, call findTopic again with the left half. If the topic is later, call it again with, and keep doing this until you find the entry. And this is a fairly natural way of thinking about the algorithm that we call binary search. Why binary? Because we split things in two. Let's analyze the runtime of it briefly. Let's say in an encyclopedia, a maximum of C entries fit in the page. And then for each of our else things, there's only one step. It's like set the half of the book. So that's just over one, and we can effectively ignore it. Also, in each half, we are then going to call the function itself again on half of the input. What this gets us to is a recursive relationship that looks like this. And remember, we've seen some of these before. We're going to solve them using. We're going to solve this one using a slightly different technique. So the runtime of our function is the C step to look through the thing on the page plus half of whatever the current one was going to take. The big question here is how many recursive calls are there going to be over the period of the lifetime of the algorithm? Because we can only halve the number of pages so many times before we get to only one page. Also, there's a slight thing I'm missing here. For very astute watchers, you'll notice that there should be a floor function in there, because sometimes half isn't exactly even, but we're going to omit that for clarity. So this is what the series of halving looks like. It's n on 2, n on 2 on 2, n on 2 on 2 on 2 on 2, all the way to 1. And another way of writing this is n, then n on 2, then n on 2 squared, then n on 2 cubed, etc., 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 all the way till we get to n on 2 to the k. And we know that the very last term is going to be equal to 1 because we're going to get back to a single page. And so n on 2k is equal to 1. Mess things around, take the log, and we get k, the number of times we do the halving, is log n. And we know that in each step, we are going to do C operations because we have to look through the elements on the page. So overall, we are going to do C log n plus C steps, which is the same as big O of log n. So binary search takes only log n steps, which is much, much faster than our runtime for linear search, which was big O of n. For example, if n is 1024, and we're doing, and we're in base 2, if n is 1024, and we'll say that the constant out the front of both binary search and linear search is 1, and obviously it's not exactly, but for the sake of argument, linear search, it would take us 1024 steps. For binary search, it would only take us 10 steps because we only have to do the halving times, whereas for linear search, we have to go through every single page. Yeah, this is just restating what I just said. We will leave the correctness proof of binary search to the next lecture, other than to note that we're going to do the same kind of thing we did before. We're going to have some invariant, and I'm not going to describe this invariant now, and then we will put the invariant in our code in order to describe at each step something that we believe is true, and use the fact that we know that this is true both at the start and at the end in order to come to a conclusion about the algorithm itself. Thank you all very much for being here today. Together. I know that some of you may be a little bit concerned about assignment 1. Please stay calm. It's well within your capabilities. We're here to support you, and please shout out to us as you spec, which might take a little bit of time. Think clearly, and if you still get stuck, for you on Piazza, on Grok, and as always in consultation hours. And with that, we are done for today, and I look forward to catching all of you tomorrow. Thank you very much.
Thank you.
Pleasure.
Thank you.
Oh, and questions as well.